What you got? Okay. You know what to do. All right. So everybody find a spot in here. So HJ, find yourself a spot where you're comfortable. There are 5 spots at that table back there. There's room in here. There's this chair, and then there's that folding chair, which can be pulled up like kind of right here behind this table if that's where you're more comfortable. Wherever you want to go. Oh, this was about to leave the backpack. Do that. So wait, this backpack is there. What that is, maybe. All right. All right, are these stalls here? Here. Yeah. All right. You're good to go. If your parents are picking you up, don't leave the guard. You can see them, okay? All right, excellent. All right, we're settling in. Everybody's finding a spot. It's warm in here because there's so many bodies. So I'm gonna turn the fan on. Maybe. Yes, I am. Excellent. All right, who's still coming? I'll make sure everybody's got a spot. Who are we missing? Oh, we're just missing Jordan. No? Okay, we've all got it. 3, 4, 6, 1, 2, 3, 4, 6, 7. Jordan? Jordan, 9. Still not here. Yes. Okay. All right. Ready to have a good summer? Cool. All right. So not everybody knows everybody. We're just gonna take a second to introduce ourselves because we have some newbies. So I'm Miss Danny. I'm Easy. Grace. This is Grace. How long have you been here, Grace? 2nd year. And you are? Yeah. Leah. And do you know her? Yeah. Okay, they're sisters. This helps. And this is your 1st year.
I'm Claire. This will technically be my 3rd year.
Yep.
And
2nd in a row.
Okay.
Well, she did a junior class once. Yep. Okay, excellent.
My name is Maddox, and this is my first.
Maddox in his 1st year. Maven's his sister. Okay, because we've got siblings. Ms. Ridley?
I'm Ridley. My 4th year.
4th year. Ridley's done after this year. This is it. And you are a senior this year, right? Are you not a senior yet, are you? Yeah, you're my only no, Lucas. You're my only real senior, aren't you? I think so. Wow. Okay.
I don't want to be. I don't want to leave.
Well, I appreciate that. All right.
I'm supposed to do it.
All right. Would you like to introduce yourself? This is HJ, and this is her 1st year. Yep. All right.
I'm Isabella. This is my 2nd year.
Isabella.
I'm Lucas. This is my 4th year.
And you were related to anybody else in this room? Xander. Yeah. Unfortunately, this is your 4th year too, right? 4th for you? Yes. All right. And Jordan?
Yeah, I'm Jordan. This is my 4th year.
4th year. Yep. And?
I'm Xander. This is my 4th year.
Yep. So Ridley, Xander.
Where's my folder?
Oh, good question.
Is it right there on top of the speaker?
Oh, yes. Thank you.
On my.
There you go. So Ridley, Xander, and Jordan.
My head's
Okay.
full.
Have a great one. Do you need some assistance? Yeah. Here you go. All right. There you go. Bye. See you next week. So anyway, Ridley, Xander, and Jordan and Lucas will be leaving us after this year, which is wild to me. They will have done all 4 years. So that's outstanding. And Ridley is our only senior, so she's on to big different things after this.
Full-time college.
Yes, full-time college. We had a bunch last year that left. Last year we lost a lot. We had like 6 or 7 that didn't. Oh, sorry. That didn't. We lost. So anyway, but only 1 senior last year, which was Drew. So that's my youngest. So there we go. So this is our 9th year doing this program. And that means it is the 3rd time we've taught earth science. So I want a big thing for y'all to note in particular is after 9 years of teaching this, the textbooks that we started out with They're older, right? These are older textbooks. For most of you, the book is older than you because it was published in 2008. So for most of you, this book is older than you, but it's okay because the earth is a whole heck of a lot older than the book. All right. The only things in there that are different are certain technologies. And when we get to them, we'll address them. That's it, really. Because the rest of it's, it's old stuff. All right. So we're going to roll through this. Now, I was showing this to the juniors earlier. I know it's ice cube trays, but your names are on them. All right. Now, the way this works is when I ask questions, I give everybody a chance to participate. I like everybody to participate at least once. Some of you are people don't participate too often because you just don't like to talk out loud. That's okay. If I find there are certain people that like never talk, then what I'll end up doing is I won't let anybody else answer a question until that person answers. And I don't care what you say. What do you say if you don't know the answer?
Carrot.
Carrot's the answer if you don't know the answer. The reason behind that is because I understand some people get anxious when answering questions in front of people. And I used to work at a school for kids with special learning needs, and our math teacher did not understand that you can't just put a student on the spot because you may not get the answer you want. So he asked something like, what is 8 times 2? And pointed to this kid, and this kid answered carrot because that was the first thing that came into his brain. So that has been our answer for I don't have an answer. I'm going to give you carrot. You're still going to get a coin. Now, these are pennies, and pennies go in the bins. Why? What do we do with the pennies, people? What do we do? Skittles on the way out the door. So I do bribe you with candy for participation, and I'm not ashamed to admit I will bribe every one of you. But it's good. It gets us going. All right, and if we have time at the end of class, we'll play our beach ball game, but only if we get through all of our material. And our beach ball game is just an icebreaker, get to know you game. Definitely didn't have time with the juniors, and that was because some of them have yet to learn how to take a turn and raise a hand. You may have observed this, right? Some of you really observed this. All right, that will take them time and they will learn. We do try to raise hands. We do try to take turns because a lot of homeschoolers are just not used to it. They're not used to being in a room with other kids, so they're not used to taking turns, and that's fine. We'll learn. We all learn. All right, so what's science? Let's get into it. So if you did your lesson, your kind of how to science lesson, you probably saw something like this. So science is a system of knowledge and a method. It is a thing. It is a what you know. It is also a what you do. It is both a what you know and a what you do. So science begins with something and ends with something. What might it begin with? Jordan, were you waving? You're waving?
A hypothesis or a thought.
Getting there? Yeah, hypothesis, a thought. If what does it mean to like wonder? What's another word for to wonder about something? Yeah. Question, that's good. So we're looking for curiosity, being curious, right? So if you're curious and you form a hypothesis and you run an experiment, at the end you get a discovery, all right? And sometimes it's you're confirming something you already knew. Sometimes you're discovering something entirely new to you. All right, and what is the use of knowledge to solve practical problems? What do you think? Technology. All right, so when you think of technology, what do you think of? Somebody just say it. This is a just blurt out. What's technology? Example. Trains.
Cell phones.
Cell phones. Computers, right? So most of you are thinking pretty complex things, but your pencil is technology. Your shoelaces is technology. If you kept wearing shoes that kept falling off and you thought, I know my knowledge tells me that if I tighten it around my ankle, it won't fall off, but I also need it to be loose enough to get my fat foot in it, then you might think, well, maybe I could tie it. And then now you've created new technology, shoelaces. Anything like that is technology. So science and technology are interdependent. What's interdependent mean? Anybody know? Isabella? Yeah, one depends on the other. And advances in one lead to advances in another. So we talk about sometimes there are accidental inventions. So my favorite accidental invention was Stephanie Kwolek. Does anybody remember what Stephanie Kwolek invented? So Stephanie Kwolek, raise your hand if the story becomes familiar. Stephanie Kwolek worked for DuPont, and she was tasked with creating a new type of polymer, which is like a long chain molecule. Do you remember what she did? She accidentally invented Kevlar. Yeah, and what is Kevlar used for? Yeah. Bulletproof vests. All right, so She accidentally invented Kevlar and it is used for bulletproof vests. So she saved lives accidentally. Good for her. All right, so we divide science up into different categories. We have our formal sciences, mathematics, logic, and statistics. These are ones where you find 100% true answers, right? When we talk about science being settled or whether science is always true, right, wrong, that's where you find that. 2 plus 2 is going to be 4. It's going to be 4, promise, no matter what they teach of the it's going to be 4, right? All right. Now, then we have this set of sciences that are like anthropology, economics, geometry, political science, psychology. What are those, Lucas? Those are your social sciences. Social meaning how people interact with other people. And then we get into natural sciences, and that's what we deal with here. And natural sciences are largely divided into life sciences, and I just have life science there. But there's biology, zoology, entomology, mycology. There's a million of them. You can subdivide that in many, many ways. And then we also have physical science and our big subdivisions of physical science. Which one would be the study of nature, properties of matter, and energy? What do you think, Xander? Physics, very good. Which one is the study of celestial objects, space, and the physical universe? Claire? Astronomy, not astrology. What's astrology? What is it? Zodiac signs and stuff. HJ's got it. Yeah, zodiac signs and stuff. Do I have another Pisces in the room, or am I the only one? Hey, okay, that's astrology, right? Astronomy is what's out there, right? All right, and then how about identification of substances? Yes, Ridley? Chemistry, very good. And whoop, come on. And then what's this last one? Physical constitution of the Earth and its atmosphere. Jordan?
Earth science.
Earth science. All right, now in this class we're going to do number 4, Earth science, and we're also going to do some astronomy. We don't get into the crazy math astronomy. This is a tip. A lot of people that go to college and need a science credit, but maybe they don't want to be a STEM major. They're majoring in something else. I don't know, French literature of the 12th century. I don't know, something. And they're like, oh, I'll take astronomy. That'll be easy. It's just memorizing constellations. No, it's not. That's a really challenging class. A lot of people will make that mistake. They're like, oh, it'll be fun. I get to look through a telescope. And then within a week, they're going, what did I do? Why did I sign up for this? There was a kid, used to be on my older son's gymnastics team years ago, who signed up for, this was my favorite. He thought he was signing up for cosmology class, which is similar to astronomy. Do you know what he actually signed up for? What did he sign up for, Isabella? Cosmetology. Yeah. He put himself in a makeup and hair class and was like, well, that was a mistake. That's not what I meant to do. Okay, whenever you see those little guy, I try to put him on all the slides. He's not always there because I don't always remember. But this means this is going to be on one of your exams. It will likely be on your unit test. It will likely be on your midterm and or your final. So when you see him, that's when you know. All right. Now, our big ideas in the whole physical science category. What do you suppose this first one with the helmet and the hourglass would mean? It's 2 words. Where's he going to, everybody? Space. And what's an hourglass tell you? Time, space and time. All right. Now let's look at this one. We have a bunch of symbols and then an arrow. What are the symbols for? Anybody recognize any of them? What is it, Jordan?
They're like military.
They are military. What do we call those? The armed what? Armed forces. Forces and the arrow would be? Motion. Forces in motion. Okay, excellent. Now this one's a little more challenging. There's a little atom looking like thing, and then there's, what's that symbol? Who knows? Jordan.
Delta.
It's a delta. What's a delta mean? Ridley. Change. You got it. You're fine. Yes. Change. So that would be matter and change. All right. And then what do the batteries stand for, do you suppose? Xander? What do you say? I'll help you. Energy. I know that's what you were going for. Energy. These are our big concepts in physical science in general. So this is where it gets a little interesting. When you start defining these terms, you will find the other terms are part of their definition because they're all interdependent. There's that word again. So if you define space, notice the color of these, right? Like that one's hot pink, white, gray, blue, right? You'll see, I put the words in those colors so you'll see them when they pop up. So space, you've got, continuous expanse or area, dimensions, height, depth, width. in which all matter exists because space contains matter, right? Unless it's like a vacuum or whatever. So there you have matter as part of the definition for space. If you look at time is probably the hardest one for, if I said define time, you would probably have a difficult time defining it without using the word time, right? Because it's very, or without using a measure of time, seconds, because it's hard. So time is defined as measured or measurable period during which an action, process, or condition exists or continues, or a non-spatial continuum that is measured in terms of events which succeed one another from past through present, like a timeline, that kind of a thing, right? So that's how we define time. Forces push or pull on an object, that's matter, right? Resulting from the object's interaction with another object. If I kick a ball and it moves, it's moving because it interacted with my foot. So it's matter interacting with matter. Then you've got an influence that can change the motion or velocity of matter. So there's change, right? The motion or velocity of matter. So if I took my finger and I push this bucket, I have just done what? I have changed the velocity of this matter. What's velocity? Who remembers? Anybody? Physical science people. Come on, that's at least 4 of you. Do you remember?
It's a vector with
Good.
motion.
Yes, it's a vector. It's motion with direction, right? And we show vectors with arrows. So there's, what do you know? There's an arrow talking about motion. All right. And then how do you define motion? Change with the time, there's time again, and position or orientation of a body of matter. Again, if I move the bucket, did it move instantaneously or did it take me time? It takes me time to move it, right? This is not a port key. We're not beam me up Scotty. Things actually take time to move over a distance, and the matter's position changed over time. That's motion, right? And then it's a phenomenon in which an object or matter changes position with respect to space and time. So not only did it change position over time, it changed position. It's closer to my laptop. It's further from my laptop. It's closer. It's further with respect to other matter, right? So how do you define matter? This is the easy one. Matter is just stuff. It's everything. Everything's matter. It's a material substance that constitutes the observable universe together with energy forms the basis for all objective phenomena. Phenomena being your plural, your plural of phenomenon, right? So everything that you see happening in the world around you is because of interactions with energy and matter. Everything, chemical reactions, the way that you're sitting on the couch, it's how matter is interacting with energy, right? And then anything that has mass and takes up space is matter. That's your basic definition for matter. Does it have mass? Does it take up space? Mass is what? It's how much matter there is. So those two are completely interdependent, mass and matter. It has mass, it takes up space. All right, and then how do you define change? How would you define change? Somebody want to give it a try? That's a fun one. It's like trying to define time, right? How do you do that? Nobody even wants to give it a stab because it's hard. Transition from one accepted theory to another, from one employed method to another is change. Process in which one or more substance or matter is altered into a different substance. That's an easy one. Like a chemical reaction causes a change. If you put baking soda and vinegar together, what happens? What happens? What do you get? Yeah, why? What's being produced there, Ridley? A gas. So you've put two bits of matter together and it's created a new type of matter. That's a change because it's a chemical reaction. An alteration, transformation, modification, substitution, these are all other words for change, right? And then how do you define energy? Energy is the capacity to do work. If you have no energy, you cannot work. If you have no source of energy, so like the third example there, it says a source of usable power. So gasoline in your car, let's say you don't drive an electric vehicle, gasoline in your car is your source of energy. If you don't have it, is your car going to go anywhere? Nope, you're stuck, right? But here's the other thing. Like the second bullet point says, property of a system that diminishes when the system does work on any other system by an amount equal to the work done. So if you get in your car and you start driving, now the gasoline is doing work on your transmission, on your engine, and then that's turning your transmission, and then your wheels are turning and your car is doing work on the road. And as it's doing work, what happens to the amount of gas in your tank? It diminishes. There you go. All right, perfect. All right, our big ideas in earth science are going to be systems. Earth is a system of systems within a system. Great example. We have a hydrosphere, right? It's all the water on Earth. So it's lakes, rivers, streams, aquifers, water vapor in the air, clouds up in the sky, in the atmosphere. All of that is hydrosphere. Okay, a system within a system of other systems. Okay, so you have the hydrosphere, that's a system. That's a system on Earth. What system is Earth part of? A solar system. Okay, so we have a solar system that Earth is part of. All right, and then what would the solar system be a part of? Yeah? Galaxy. And then what would a galaxy be a part of? The universe. Yes. So I mean, yeah, it's just like a Russian doll, right? Systems within systems. You know those little dolls, right? Little wooden dolls, you open them up, there's another one, you open that one, there's another one, you keep going. Right. So then you have energy. The flow of energy drives the cycling of matter. Okay. Great example. There's a puddle outside. You look at the puddle, it's got water in it. Energy's coming down from the sun. What happens to the water in the puddle? It's going to evaporate because the matter now is cycling. It's changed form, right? It was a state of liquid. Now it's a state of gas. And okay, energy's there from the sun. It's cycling it. It goes up into the atmosphere. It gets into a little cloud and starts collecting with other little tiny droplets of water. And then it gains a lot of mass. And then what happens? What happens when it gets too much mass up in the sky? It's good, yeah, rain or snow, you're going to get precipitation. What is the energy there? If it's way up here and it's coming down here, what's that energy? Gravity is the force. What kind of energy? Does anybody know? Until it falls, it has potential energy, which is, so you're right. So it has gravitational potential energy. And then when it falls, it's gravitational energy. So gravity is right, but your term you're looking for is gravitational energy. So that just cycled. Multiple kinds of energy came into a system and the matter within it cycled. Life in the environment, including human life, influences and is influenced by, I cannot speak, the environment. My main influence today is that it's like 100 and goodness knows how many degrees out there with the heat index, and I'm not going. It is influencing my life for sure.
Actually a lot cooler than it was yesterday.
I know, yesterday I'm sorry, that was Hades.
Hate crime level heat.
Thank you, ma'am. Hate crime level heat. I will go with that from now on. That is absolutely correct. All right, and then you have the unchanging drives change. Physical and chemical principles are unchanging, and they drive both rapid and gradual changes in Earth's system. If I took, I could use the pennies, but they're kind of light. Let's say I took that big crystal ball that I have that sits up there. That's just kind of interesting to look at. I don't do anything with it, but go, that's pretty. And bring it out when I do my Harry Potter party for Professor Trelawney. If I let it go, what's going to happen? Gonna hit the floor, right? It might break, but it's definitely going to hit the floor pretty hard, right? It's going to hit, that's pretty solid. I don't think it would break, but it would hit the floor. So if it hits the floor, what's unchanging? Every time I drop it, what's going to happen? It's going to hit the floor every time, right? I'm going to open my hand. It's going to go down. Because why? Because you said it before, gravity. Okay. What will change eventually? Eventually it will do what? You said maybe shatter. What'll happen to my floor? Yeah, I would jack up my hardwoods if I did that, right? So this unchanging, this fact that if I open my hand, it's going to fall every time is going to cause change, right? And you'll see that a lot in our science, because when we talk about different types of erosion over time, different types of land movements over time, the way rocks change over time, it's always unchanging principles that cause the change. And then lastly, modeling and mapping. Can you see the entire solar system with your eyeballs? No. Can you conceive of it? Yes. How? Because you do a what? A model or a map. Can you see the entire globe with your eyeballs? No. Yeah, but you can look at a globe and you can look at a map. Models and maps are necessary for things we can't see or conceive. How about a cell? That's the opposite of the solar system and the Earth. It's tiny, tiny. Can you see that with your bare eyes? Yep. But if you had a microscope, you could see more of it. If you didn't have a microscope, somebody could show you a diagram and go, here's what a cell looks like. All right. Science and perspective. Like I said before, science is a process and a body of knowledge. It's a what you know and a what you do. It is both things. Being skeptical. What does this mean? What does skeptical mean? Anybody take a stab? Oh, Max, you want to take a stab?
To be questioning.
To question things. Yes, exactly. If I came in here today and told you the sky is purple and you all went, okay, you said so, I would be very upset with you all. That's not very skeptical. I'd also think you're crazy. So yeah, you have to be skeptical. Question everything, right? Always question as you go through. That will make your whole life better if you are skeptical, not just scientifically. Be skeptical when the guy, personal experience, when the man calls you and says, I'd like to talk to you about replacing your old windows in your house, but I need both you and your spouse present, be skeptical of that. And then when they walk in the door and sit here for 4 hours, be skeptical of that. And then when they leave their model window on your kitchen counter and go out to their car and say, I'll be back in a few minutes while you guys decide, be real skeptical and don't buy those windows. Be skeptical, right? Okay. Ask questions. Like you said, asking questions, being curious, always ask questions. Like, why did you stay here for 4 hours? This is the worst sales tactic I've ever seen. And then believe in the process. Okay. This is the difference between scientific literacy and illiteracy in many cases. The process is trustworthy. Are the data and results always trustworthy? No, because human error, what else? What else influences conclusions? Yeah. Bias. There you go. Bias is a big problem. Okay, of the 4 disciplines we do here, Earth, physical, chem, bio. This is the one we focus the most on how you determine what is a good source, how do I analyze this data, how do I remove bias, someone else's and my own, and how do I come to my own conclusion based on data, not based on emotion, not based on somebody telling you and you thinking they're an authoritative source, so I'm going to do what he says just because he's an authority, right? This is about you learning. The way we do that in this class, it's because some of Earth science labs are like really dry. So I'm like, we're not doing those. So what we do instead is we take the opportunity to go through 4 documentaries together as a group. And they are all climate change documentaries. And there's the first one and then the answer to it. And then the first one sequel and then the answer to that. And it's fascinating because you'll be presented with data in the first one. They're going to tell you, this is our data and these are the conclusions from that data. And then when you watch the second documentary, they're going to say, here's the same data. Here are our conclusions from that data. And they're completely different. Data's the same. Conclusions are different. Biases are different. So that's where it comes in. You need to have your own, you need to be aware of your own biases and certainly your sources, right? All right. How do we use a scientific approach? So how do we define what's an organized plan for gathering, organizing, communicating information? What's this one? Xander? Yep, scientific method. The goal of any scientific method is to solve a problem or better understand an observed event. Scientific method, right? It's not a straight line, it's a process. So information you obtain through your senses is what, Claire?
An observation.
An observation. It's not just what you see. We like to think of observation as what you see, but it's more than what you see. If you were a witness to a car accident, you might be asked what you observed. You could say, well, I saw the red car hit the blue car, but that's not all you observed. You heard the red car's brakes squealing because he stopped too hard and the blue car rear-ended him or whatever the case was. You smelled the gasoline when it started leaking onto the road. These are all observations and they're important. So always keep in mind, it's not just what you see. Like a lot of you noticed with your little box, it had a smell. It was magnetic. These are all observations. So it's not just what you see, anything with your senses. And what's a proposed answer to a question? There you go, a hypothesis. All right, now, scientific method is an ongoing process. As you test things, as you run data, you may find that you need to revise your hypothesis. You may find that you need to revise your method, your steps. You may need to change your variables. It's a process, but it's not a straight point A to point B one-way situation. It's more of a logical continuum, but you have to do it in an organized way. You can't just be haphazard about it. Okay, who came up with it? Lots of people, actually. You go all the way back to Aristotle. He had an inductive deductive method that he used inductions from observations to infer, which we talked about before, general principles, deductions from those principles to check against further observations and more cycles of induction and deduction. This is how Aristotle worked. That's the beginning of like good scientific thought. Okay, then look at, we're moving now way later, because Aristotle, what we got, 384 to 322 BC. Now we're 964, 1040 AD, right? So this is Ibn al-Haytham, and this guy lived in like Iraq, Egypt, Arabia area. So his scientific method, it was observe, define, hypothesis, test it, assess and analyze results, interpret data, publish findings. That's almost exactly the same as how we do it now, right? So this is how we're getting there. And then we got Francis Bacon, who's English. Look at how much further we are ahead now before we get a big advancement. 1600s. And he says, in order to test potential truths or hypotheses, Bacon devised a method whereby scientists set up experiments to manipulate nature and prove their hypotheses wrong. So the point was to prove yourself wrong. Where's the value in that? Why do you want to prove yourself wrong? Discovering new knowledge, definitely. Anybody else? Why would you want to be wrong?
It's easier to prove something that it's easier to prove that something is not the case than to prove that it is.
That's a good point. Yeah, that's a very good point. There you go. And then our dude, Galileo Galilei. And these guys are working at roughly the same time, right? They're living in the same time period together. So he pioneered experimental scientific method that was first used a refracting telescope to make astronomical discoveries. And he often referred to as the mother of modern astronomy and the father of modern physics. What was his big discovery? Anybody remember? Yeah, do you know?
He created the geocentric model.
Not geocentric. You're there. He disproved geocentric.
Oh,
Heliocentric model. Okay, meaning prior to him, one of the accepted possibilities is that the sun revolved around the earth, which we look at now and go, what? But he was the guy who proved that the earth revolved around the sun. So heliocentric, sun in the center. Yeah, Xander?
The last sentence of the thing on Ibn Haytham.
Yeah.
is how it
Oh, you want a brownie point for a period. You know what to do. What's a brownie point? Explain for your new classmates.
If you find a typo in or the binder or
Anything. Yeah, anywhere.
then you can like write it down and turn it in and you get a brownie point, and if you get like 20 or
25.
you get brownie.
We bring brownies. Yep, it's catch me when I'm wrong, right? All right. So variables. What is the variable that can be manipulated by the experimenter and can cause a change? So it's what I change. What is this one? Is it Lucas again? What is it, Lucas? There you go. You will find this called both independent and manipulated, depending on what textbook you're using. It makes sense. Manipulated might make a little more sense because it's what you are changing, but independent is also the kind of the older term for it. So a lot of textbooks will use it. I always grew up with independent and I started seeing manipulated years later, but it's what you change. What is the one where it changes because of what you changed? It's what you observe for changes, Ridley. Dependent. It depends. This one where depends makes sense. It depends on what you've done. It depends on what you've changed. And it can also be called responding because it responds based on what you changed. And what is the thing we keep the same? Claire? Control. And that is super important. You have to have a controlled variable. So if you did the how to science lesson that you're supposed to do before you come to class, We talked in there about an example of an experiment that was not controlled. What was the example I used? Does anybody remember? So if you have a headache,
Oh, yeah.
okay, if you have a headache and you hypothesize that putting a cold compress on your head will make it go away, and then you go in your room and you turn off the lights and you lay down in bed and you take a Tylenol and you put the wet washcloth on your head and lay down, and poof, your headache goes away. Can you say the washcloth did it?
No.
No, because you laid down, you turned off the lights, you took a Tylenol. All of those things could have contributed to the change. So you need everything to be the same except the independent variable. So that would be, I go about my day with the washcloth on my head and I keep doing what I'm doing and nothing else changes, right? That would be a truly controlled experiment. So if I said, I hypothesize that girls are smarter than boys, and I give a pop quiz on lesson 1, and most of the girls in this room score higher than most of the boys, I'll say, oh, girls are smarter than boys. Is that a good hypothesis? Is my experiment controlled? Okay, it was a decent hypothesis. I could have tested it. Why was my experiment not controlled? What are some things that could have contributed to the girls scoring higher than the boys? Claire.
Whether the girls studied.
Whether the girls study more. Lucas. Depends on what the quiz is about. Okay, yeah. How do I know if the boys even read the lesson? I don't know. Maybe you boys didn't read the lesson. I don't know. You know, there's lots of things that what if one of the boys forgot his glasses and failed the whole thing? What Jordan came in with no glasses? And no good, right? It'd be no good. It would not work, right? That would not, you could you do it? Could you do a quiz if I took your glasses away? I don't think he could. So that's just ridiculous. We don't do that. That's ridiculous. We have to control our experiments. All right, now, and remember that one. If your data doesn't support your hypothesis, you can revise or rewrite it. You can your hypothesis, that is, or you can conduct a new experiment, test a new hypothesis. There's lots of things you can do. Theories and laws, all right? A rule or principle that always works the same under the same conditions is what, everybody? It's going to work the same. What is it, everybody? Say it. That's going to be a law, right? And a well-substantiated explanation is going to be a what? A theory. The way we do it in class is this. This is the way we define it, so it's nice and easy. A scientific law tells what happens, a what? A fact. A scientific theory does what? Explains why something happens. An explanation, right? Now, this will be, I'm telling you right now, every midterm, every final exam, every unit 1 test you ever take. And when you take, there are a few things that I want you to actually like memorize, like phrases that you have to memorize in this class. This is one. All right. What's the other really big one? What is it?
The 3 rules of science.
Why science is never settled. There are 3 points. You do need to memorize them. And if you write, there's always more to learn. That's a no. You don't get credit for there's always more to learn. There are 3 points. They were in your starter lesson, right? In your how to science lesson. Know them. Know them. They're important. This is foundational. That's foundational. The why science is never settled. This is foundational. If you don't understand those things, you can't do the rest of science well. Like in good faith, you can't. You have to understand them. All right. So now, models. We talked about models. Can you see that carbon atom with your eyeballs? Nope, but you can model it, right? Can you see the layers of the earth with your eyeballs? No, but you can model it. So models are important.
Sentence I don't have repeated.
Son, you better write these down. Diagrams and charts and graphs and things of that sort. So graphs are where you do, who has done algebra yet? Just for a show of hands. Everybody knows, or most of you are going to know X and Y. Which way does X go? Which way does Y go? Right. Most of your graphs are going to have your X-Y relationship going on where you can plot bars, or you can do like this is a graph, this is a graph. Charts are diagrams of information in the form of a table graph or diagrams. So charts can be graphs, but not all graphs are going to be, that's right. Right. Okay. There we go. Measurement. All right. When you cook in the kitchen, or when you drive your car, or when you go to the doctor and you ask them how tall am I, they might give you centimeters, but usually you're going to be dealing with feet, inches, miles, tablespoons, gallons, pints, right? there are actually really good practical arguments for why the imperial system is good. There's some really good solid arguments, and it's what we use here, so it's what we're familiar with. Like if I say it's 100 degrees outside, you know what that feels like, right? But that's Fahrenheit. The problem is they don't relate well to one another, and they're hard to work with because they're not good round numbers, whereas SI units, metric is all base 10. So we use the base 10s. It's weird when you start, and I admit I've been teaching science now, well, this is, well, shoot, 10 years if you include the other stuff I've done out, no, 11 years outside of here. I still, if I'm on Amazon and it says something is 53 centimeters tall, it's hard for me to visualize it. Where if you say something is 12 inches tall, I know exactly how tall it is, right? Because you don't live with it. You will get used to it. And I promise you, it will be easier than trying to deal with inches and yards and pounds and whatever else. So they're SI units because it stands for Système International d'Unité. It's French. I don't know why. We picked the French one. What's the one for length, everybody? What's our SI unit for length? You can just say it. Meter. What's the SI for mass? Gram. What's the SI for weight? It's not a trick question. It's also gram. There's our gram again. How about area, which is 2D? Meters squared. Think about it. If your length is meter, remember areas like I want to tile the floor. I need a length and a width. Those are both length measurements. So it's going to be meters squared. So then what's volume going to be? Meters cubed. Very good. Length, width, height. So area, I want to tile the bathroom floor. Okay. Volume, I want to fill the entire bathroom with party foam all the way to the ceiling. Volume, right? All right. Density is how much mass is contained in a space. How do we do that one? By now? So we do that in kilograms or meters cubed, right? Now, density is like, for those of you who haven't had too much experience with density, if I had a marble and I had a cork ball that was the exact same dimensions as the marble, and I put them in water, the marble is going to be more dense than the water because there's more matter packed into the marble and it's going to sink, whereas the cork marble is going to float on top because there's less matter packed into it and it's less dense than the medium it's in, than the water it's in, right? Time, what do we measure time in? Seconds. And temperature we measure in primarily Celsius, right? And you don't say degrees Celsius necessarily. This is here because people are like, who, what? But yeah, you can just say it's 35 Celsius. You don't have to say degrees Celsius. What are the other temperature scales? We have other ones besides Fahrenheit, which we don't use. What are the others, Isabella? Kelvin. What's the special thing about Kelvin? Goes way below. It goes to absolute zero. And what's supposed to happen at absolute zero? What?
Zero.
Yeah, zero motion of particles, zero molecular motion. Can we get there? Do we have a freezer that'll get us there? No. All right, and then we have our base units, and then if we're dividing by 10 or multiplying them by 10, so you can have a decimeter, which is a tenth of a meter, or you can have a decameter, which is 10 meters. You can have a 100th of a meter, which is a centimeter, or you can have a hectometer, which is 100 meters. Same thing for a thousandth, right, which is milli, and kilometer, kilogram. You do get measured in kilograms when you go to the doctor. You do get measured in centimeters, though it probably doesn't mean anything to you, so they come back and tell you your pounds and inches.
It might be first in the book because it says divide numbers by 10 if you're getting bigger. That one says divide if you're getting smaller. Yeah, you just like switched it around than the normal.
Where, here?
Not
Here I did?
because it's not King Henry died.
Oh, yeah. So yeah, you can go either direction with it. When you look at it in the book, it's just they're flocked on other sides. You're still dividing or multiplying, but so the dividing and multiplying are the same. But yes, it's in the book. It'll show you. There's like a King Henry died suddenly, whatever unit, unusually, whatever you want to use, drinking chocolate milk. It goes backwards up here, but in your book it goes the other way. It's the same thing, it's just reversed. Yep. So that's another one to remember. We'll be using it a lot. So scientific notation, we won't use as much in this class. We might use it when we get to the space units. We're talking about how far away things are because it takes very large and very small numbers and makes them easier to deal with. You'll do like 3 times 10 to the negative 18 at the top there instead of writing all those flipping zeros because that's easy to mess up, right? right? Or at the bottom, 3 times 10 to the 18th power, because that's a whole lot of zeros. That's real big. That's real heavy, whatever that is, right? So if you notice, I use the number 3 in this example for a reason. And there's patterns here with the numbers. Look at the exponents. 1, 2, 3, 6, 9, 12, 15, 18. What's the pattern? Once you get past 1, 2, then you get to 3, what happens after that? 3, 6, 9, 12. What is that? It adds 3, it's 3, right? Yeah, they are multiples of 3, right? So why do we do that? Okay. We do that because when you write the number, say for example, you want to purchase a new car and it's $35,000. How do you write the number? 3, 5, comma, 0, 0, 0. Your commas go after chunks of 3, right? 3 digits, comma, 3 digits, comma. 1, comma, million, 253, comma, thousand, right? 128 or whatever your number is, right? That's where your commas go. So that's why we tend to use multiples of 3 if possible, not always. All right, so Earth systems. Let's get into the meat of Earth science. So we have lots of different systems on Earth. A system is a group of interacting or interrelated elements that act according to sets of rules to form a unified whole. Oh, that's fun, right? Lots of different things that interact, like when we talked briefly about hydrosphere, which we'll see again in a minute, and we talked briefly about exchange, how energy energy that is a force, right, is going to change matter. We talked about how you're going to get evaporation, then you're going to get condensation, and then you're going to get precipitation. That's all a process of things interacting with one another. A system surrounded and influenced by its environment is described by its boundaries, structure, and purpose, and expressed in its functioning. All right, let's look at some examples. We have thermodynamics. This is my favorite one because I think this is just wild. But we discovered our first and second, third laws of thermodynamics, and then we're like, oh, there's a fourth. Let's call it the 0th and not the 4th. I love that. It's like one of the weirdest things. But yeah, so, and your 0th law is really the obvious one. It's the most obvious of them all. So your first law is that energy is conserved, right? There's conservation of energy. If you put energy into a system, an equal amount of energy is going to come out of the system. Your second law is your entropy law, right? It's that heat flows, or energy in general, heat's going to flow from warmer to cooler, right? If you touch the glass table, it's going to feel cold to you. It's really the same temperature as the room. But if you touch it long enough, it's going to warm up where you put your hand, right? Because the heat is going to flow. If you put ice on a table, it's going to melt. And then your third one is that as the entropy of a system approaches a constant, as a temperature approaches absolute 0, that's the whole absolute 0 thing, stop moving. But then this is the obvious one. And it says, the 0th one is the obvious one. It says if 2 systems are in equilibrium with each other, so system A and system B are equal to one another, they're in equilibrium with each other, and system C is in equilibrium with system A, then system C must also be in equilibrium with system B, right? It's kind of obvious, but we state these things in science because we want to make sure everybody's clear about what's happening. So another thing to talk about systems and energy exchange that applies to thermodynamics is open systems, closed systems, isolated systems. An open system exchanges energy and matter with its surroundings. A closed system only exchanges energy, but not matter. And an isolated system doesn't exchange energy or matter. Examples. So, open system, great example, a pot of water on a stove. What matter is it exchanging with the environment? What? Water vapor, okay? So you had liquid water in the pot, it's becoming water vapor. There's an exchange of matter, correct? What energy is being exchanged? Heat, right? You got heat being exchanged, all right? So you've got heat and water vapor being lost to the air. So there you go. You've got an open system. A closed system, you got a balloon, all right? You fill the balloon with hot air. Is the air going to leave the balloon if it's closed up tight? No, the air is not going to eventually, because it's not perfectly, but you leave balloons long enough, they shrivel. But in general, you got a balloon. Let's make it a perfect balloon. The air doesn't leave it. So no exchange of matter. What will happen to the warm air in the balloon eventually? It will cool because it's exchanging energy with the environment. So it's a closed system in that it's keeping its matter, but it's not keeping its energy contained. Now, this one's a little different. Your isolated system, the best example, one of the best common examples we have, is like a thermos vacuum seal kind of water bottle situation where you put your spaghetti, you warm them up, put your spaghettios in it, and you take them to lunch and you bring them here to eat them. I don't know who eats those besides my kid. Kind of weird. But anyway, yeah, Isabella's like, ew. All right, you put your spaghettios in there, you bring them to science class, and when you open them up, they're still warm and they're all in there, right? None of them, they didn't evaporate, they weren't exchanged with the environment, and it kept the heat. But if I left that thermos on the counter for 3 days, will they still be hot? No. So there is still some exchange. This is really hard to create and make it a real, true isolated system. All right, you got the physical Earth. What do we call this system? We call this the geosphere. Ah, here's Greek and Latin. We get Greek and Latin roots all the time. Sphere means what, everybody? Ball. Geo means Earth. Earth ball. Okay, Earth ball is our geo. It's what it is, Earth ball. All right, so Earth ball is our Earth and its layers and Earth in general. Then we get Earth's atmosphere. Okay, there's a Greek and Latin root there. What is atmos? What is, you know? Air. Yeah, it's like air, like particles, air, right? So atmosphere, air ball, particle ball, air particle ball. All right, there you go. And then we have, what's this one? The water on Earth. We've said it a couple times. What is it? Hydrosphere. Hydro means water. Sphere means, so it's water ball. Okay, there you go. Water ball once again. All right. How about the living things on Earth? What's that? Claire.
Biosphere.
Biosphere. Bio means
Life ball.
life ball. She says it. It's life ball. Look at the life ball. You look outside, you're seeing the life ball. Isn't that good? That's so nice. All right. So here we are. Geo and sphere give you Earth ball, right? Atmos and sphere give you vapor. There's an exact word, vapor ball. Sphere. Hydrosphere gives you water ball. And biosphere gives you life ball. Right? There you go. Uh-huh.
If there was a thermostat, it's gonna be fireball.
Fireball. That would be good. I'd like fireball. So let's just review a little bit of lab safety. We kind of already went over these, right? So you be sure that you do your assignment on recognizing lab safety because that will keep you safe in class. Most of the time in this class, we don't use flames too much. So it's always good to, I know, it's always good. And anybody with long hair to keep I live this way. I always have a hair tie on my wrist. It's smart to have. Always good to have good shoes in case we're going out, but closed-toed, something that you're not going to mess with. We are going to go rock hound the river at some point this year. We'll be rock hounding the river, which means we have to walk all the way down to the river. Okay, the hooch is right here. Chattahoochee's right here. And when we do that, I will give you a warning. You can't wear flimsy-soled shoes because there are some sticks out there that will go like right through the sole of your shoe. My neighbor's niece did it. She was wearing flip-flops and it went right through her flip-flop and punctured her foot, which was gross. So always do that and make sure that you've gone over all these things. You know all your lab safety rules. All right, now is where we look at your binder work and we go over it. So what I'll do is I'll just let everybody answer together if you've answered them. If you haven't already answered them, go ahead and write them in. And that way you can go back and check. So this should be at the very end of your binder work or towards the end, I think. Yeah, because you had to go through that sciencey stuff first to learn about science. So find this page. So this is for each statement below, right? True or false? So Earth's lithosphere is the rigid outer shell of the planet. True or false, everybody? False. Really? Your crust and your lithosphere are kind of going to be used the same. All right. The water in Earth's oceans, seas, lakes, rivers, and glaciers makes up the atmosphere. True or false? What does it make up? Hydrosphere. The blanket of gases that surround Earth is the atmosphere. True or false? True. The atmosphere is partially molten layer of Earth's core. Everybody? Oh no, for sure false, right? Yeah, what?
Atmosphere?
Oh, Athenosphere. I'm sorry, it's very small on my screen. Athenosphere, yes. Okay. The atmosphere contains about 78% oxygen. False, right? What's the most common element in the air we're breathing here? Nitrogen. Yeah, more nitrogen than oxygen. About 3/4 of all fresh water on Earth is contained in glaciers. True. The hemisphere includes all organisms on Earth as well as the environments in which they live. No, what are we looking for there? Biosphere. The atmosphere, biosphere, hydrosphere, and lithosphere are independent systems. It's very small. Oh yeah, interdependent systems. Yes, true. They are interdependent. Yeah, they're not independent. I need glasses. Yeah.
I like scoured the whole science book and the index and all that. What is it? The
Asthenosphere. Okay, so hold that. Let me get back to you. We get through these. Okay. All right. So how does continental crust differ from oceanic crust? Who's got an answer? Who wants to give me that one? Jordan? One is wet and one isn't. Okay. Anybody else want to give Maddox? You want to give it a stab?
What they're made of.
There you go. So the book answer is ocean crust is made up of basalt and thinner and denser than the continental crust. Oceanic crust is made up of granite, is thicker, has greater buoyancy than the oceanic crust. Cool. Excellent. Now the next one is describe 3 ways the atmosphere helps support life on Earth. Who's got one? Maddox?
It provides oxygen, obviously protects the Earth-dwelling creatures from dangerous radiation emitted from the sun, and helps maintain suitable temperatures.
Okay, yep. All right. So, book answer would be necessary for respiration, protects inhabitants from harmful radiation of the sun, helps keep the planet at a temperature suitable for life. All right. Next one. What's technology? What you got?
The book, I'm quoting the book.
Yep.
I wrote it down. The application of scientific discoveries.
Yeah, there you go. Yep. Technology is applying what you've discovered, right? It can be anything from a telephone to a shoelace. All right. How about name 3 products first developed for use in space that people now use in their everyday lives? Lucas, you got one? Give me one. Ski goggles. Claire?
Velcro.
Velcro. Maddox?
Laptop.
There you go. Laptops. So anything, ski goggles, freeze-dried food, smoke detectors, ultralight materials used in sports equipment, all that kind of stuff. All right. Now, how about A, B, C, D, E, F? Number 1, suggested explanation for an observation is a what, everybody? It's hypothesis C. Organized procedure that involves making measurements and observations is, there you go, an experiment. Factor in an experiment that can be manipulated by the experimenter. There you go, independent variable, or there's that word again, manipulated, right? Manipulated variable. Factor in an experiment that can change if other factors are changed. What's that one? Dependent variable. Factor that does not change during an experiment.
Control.
There you go, your control. And standard for comparison that shows the results of an experiment are actually due to the condition being tested. Constant. There you go. All right. Using the terms below. Wear what? And a safety apron. What are we wearing? We're wearing goggles, right? And a safety apron in any experiment. Well, not in an experiment. Depends, really. Tie back long hair and what before you begin any investigation? It's clothing. Yeah, just don't wear it, man. It's not worth it. Never use what as food or drink containers? Oh, please don't. If you knew the stuff that goes in our laboratory glassware, you would never drink out of our beakers. Trust me. We put all manner of really crazy stuff. Like I'll hand you, when you do chemistry, I'll be like, here is hydrochloric acid. And it's like really pure, and don't get your face anywhere near it because the fumes will knock you out. Like you don't want to be drinking out of that. Just trust me. Don't do it. All right, know the location and proper use of what? Fire extinguisher, safety shower, fire blanket, first aid kit. Where's the fire blanket, by the way? Yep, under there. It's right next to the first aid kit and the fire extinguisher. And the fire alarm. Okay, the fire alarms in this house are all wired together. So if one goes off, they all go off. And there are 6, 8 of them, 10 maybe. My mom has them. We have them up here. They're on all 3 floors of this house, and they will all go if one goes. So it's real fun. It's real fun. Report what? Spills. Don't clean up a spill yourself. Ask me first. Yeah.
Like in scenario where when you should use a fire blanket versus a fire extinguisher.
If it's small enough and you can get to the blanket fast enough, you can usually toss the blanket over it. Most of the stuff we do is probably going to be fine for a blanket because most of it never gets out of control anyway. But if it like starts going up the pillar, we're hosing it. No, we haven't had that happen. Thank God. We haven't had any issues with that. But yeah, usually the little ones, you can toss the blanket. My mom had one on her stove that she threw the blanket over. Thank goodness she was fast. All right, so model, law, and theory. A scientific what is an idea or system or mathematical expression that is similar to an idea being explained. Model. A scientific what is an explanation based on observations during repeated experiments. What's this one, Claire?
Theory.
There you go, theory. And well, obviously your last one is going to be a law. If you see that word fact, that's a big clue, right? All right, now, what was one model of the solar system developed by early astronomers? So we mentioned this one earlier. Geocentric. Yeah, the early model held that Earth was the center of our solar system and the sun and other planets orbited the Earth. Why would people think that? Why do you think?
Because they can see everything.
Yeah, definitely some religion belief. We're going to call those bias in this case, but yeah, and definitely if you're laying there at night looking up at the stars, you got no light pollution, right? It's not like it's Atlanta's right south of you, and you're looking and you're seeing things. They move, right? They move. You don't move, they move. But if you think about how fast you're actually moving right now, it's crazy. Like you're rotating super fast. You're revolving around the sun. The whole solar system is moving. Everything's moving. Like we are all moving. What is the current model of our solar system? If it's not geocentric, it's what, everybody? Heliocentric, that the sun is at the center of our solar system. What 3 conditions must be satisfied for scientific theory to be valid? So it must be consistent with observations, must make predictions that can be tested, and must be the simplest explanation of observations. Under what conditions can a scientific model or theory change? What causes change, Maddox? Right, if you got new data that's discovered, that's exactly how you end up with the change. Okay, so now what we're going to do, first I'm going to answer Maddox's question. Asthenosphere is a layer of Earth. Let me pull up I will pull up a graphic for you because it's easier to see it that way. Whoop. It's going to be, show me a big graphic. Right here. So it's this layer right beneath your lithosphere. And it says plastic versus rigid because your lithosphere is really rigid. And what it means by plastic is it means it's somewhat malleable. Okay, so it's a little, you can mold it, it can mold a little, it can change a little, unlike your lithosphere. Okay, so what we're going to do now is we are going to play the beach ball game for the next 20 minutes, and it is a get to know you beach ball game. Most of the questions are just simple get to know you questions, but you may be the poor child like the kid we had last year who got every one of the actual scientific questions. Jordan had it the year before, but that poor Tyler last year, remember? Like he didn't even want to talk. He was so shy. He didn't want to speak, and he got the ball every time, and he got like real questions, and it was rough. I was like, oh, because it's random. Like I didn't control what he got. So we will I'll let you decide. We can do it indoors or outdoors. But if we do it indoors, it's gentle. What do we want? Do we like the heat? Do we like the air? We like the air. I love this. Okay, so what we're going to do then is we're going to make kind of, that's hard in there because those lights are down. we'll make kind of a big circle here. Let's go behind that couch so that we have more room, and we'll come around this way. And the goal of this game is to get to know each other. And the second goal of this game is not to bounce the ball off anything in the house. Like, you have to touch it, right? And we throw it very gently. And I'm going to turn the fan off because that would be fun if it accidentally hit that and went goodness knows where. All right, so I'm going to close this. So bye, Barrett. You're good. Bye, Barrett. Everybody say bye, Barrett. Okay.